Hello friends and welcome to Average Classes. So today we are going to study your module 1 chapter 2, that is your fluid statics of fluid mechanics. Okay, if you are new to the channel and you haven't subscribed to it, please do subscribe. So fluid statics, as the name suggests, okay, static means fluid is at rest. Whatever analysis we are going to do, we will think okay, the fluid is at rest and will proceed accordingly. Sir, fluid is at rest, is it? That's it. Are you going to study? See, now I am moving. देखो मैं move कर रहा हूँ. Okay, I am moving. What you can find? कि along with me this bottle is also moving. In that bottle we have water. The water is also moving. So sir, is it comes under fluid statics category? Yes, of course. How sir? But it is moving now. Correct. See, I am moving at certain velocity, so that the bottle is also moving at the same velocity. The fluid inside the bottle is also moving at the same velocity. So what is the relative velocity between the fluid and the fluid and the bottle? Zero. So hence it will be considered as fluid at rest only. That is fluid statics category. That is non-accelerating fluid. What? That means it is non-accelerating fluid. Mechanical for you gate syllabus is mainly for non-accelerating fluid only. We are not studying about accelerating fluid more. Okay, not required. But if you still want it, you just put the comment in the comment. I'll teach the accelerating fluid also. Okay. So this is non-accelerating fluid. So that also comes under which category? Or fluid statics category. Hence we have written here. It deals with fluid at rest, and fluid can also be said to be at rest if there is no relative motion between them. Next is a large quantity of fluid moving with uniform velocity also comes under this analysis. Okay. And in particularly this chapter, that is your fluid statics chapter, we will be mainly dealing with self weight and pressure force, and we are not going to deal with the shear or viscous force. It mainly because of your self weight and pressure force, and we won't be discussing much about your shear and viscous force. Now pause the video and note it down. We'll start fluids pressure. So now we'll be studying about your pressure. Okay. So let me give you an example of this pencil. Okay. Now as you can see, this pencil has a sharp end and a flat end. Okay. Now what you do? You hold your hand like this. Okay, and try to press it. Where the impression is more, you can see here the impression is more, here the impression is less. That means I am feeling some pain while I am pressing this pencil. Okay, and that pain is different for my both the fingers. Okay, for the middle finger I am feeling little more pain and the impression is little deep, whereas you can't even find any impression on the thumb finger, and the pain I am feeling is very less. Okay. Now, why is it so? Sir, because I am experiencing some force. I am pressing it, correct? That's what the word you use, press. So I am applying some force. If you use Newton's third law, every action has equal and opposite reaction. So pencil is also giving me reaction. So the reactive force given by the pencil towards the sharp end is more, and this end is less. Is it? Force is same only. Then what is playing the picture here? Area. Then who is playing here? Area. You can see here the area is less, here the area is more. Even if I am applying the same kind of force, okay, because of the area difference, the pressure on the middle finger was more than the pressure on the thumb finger. Are you getting the pressure? That's why, okay, that is one example. Let us take about this nail. Okay, now you can see this is the flat face of the nail and this is my sharp face of the nail. If I'll hit the nail like this, if you can see, if I hit the nail like this, it will go inside, isn't it? Because the sharp face is pressing against the wall. So the pressure applied by the sharp face is more. So that's why even if the force is same, this nail will go inside. Now what I'll do? I'll keep the flat face towards the face and I'll hit to the sharp face. Will it go inside? It will never go inside, even if I'll apply the same force. You understood? You understood what's happening here? That means when my area is less, okay, if with the same amount of force, even if I am applying the same amount of force, if the area is less, the pressure applied is more. For larger the area, less is the pressure applied. Okay, you take an injection, easily it goes, easily it pierces your body. Small area, more the more pressure, but force is same. But force is same. Same with your drilling machine. Same with the drilling machine. Same with an axe and you are cutting the tree. Are you getting my point? Okay, what I am trying to say? What I am trying to say? Ki lesser the area, more is the pressure. More is the area, less is the pressure when the force is constant. When the force is constant. Okay, sir, is it always the high pressure? No, sometimes we need the low pressure also. We need to reduce the pressure also. For example, if you have seen tanks देखा है? हाँ sir, देखा है, picture में देखा है, movie में देखा है. So the tanks, you have a belt, right? You have a conveyor belt. So why that belt? Why not the what you call wheels? Wheels, the area of contact is very less. Hence, tank is a very heavy, body. So it will go inside or sink inside, or it won't get the required speed it needs. Okay, wherever when you are using a belt, what you are doing? You are increasing the area. When you are increasing the more surface area, what happens to the pressure? The pressure automatically decreases. Hence, it can have a smooth, run. This is the same thing. This is the same thing with your what you call skating shoes. When you are walking in the snow, when you walk on the snow, what you will fall? Your feet will go down. But with the particular kind of a shoe where the surface area is more, now your pressure is less. So hence, even if you have a same mass, that is your body only. Okay, still you can able to move around with that shoe as it increases the area. So it's not always the high pressure. We need the low pressure also. Okay, very good. So now the question comes, sir, these are solids. These are the pressure applied by the solid. But our subject is fluids. So do fluid actually apply force? क्या fluid सच में pressure apply करता है? Yes, it does. Yes, it does. Okay, see, suppose you have a pet bottle. You have a pet bottle. Okay. Now, let me cut this. You have water here. What do you have? Water. And I have cut this pet bottle which has water into, let us say, 3 segments. 1, 2, 3. What happens at the layer 1? Layer 1 supports the weight above it. Correct? Layer 2 supports the weight above 1. Layer 3 supports the weight above 2 and up. So we can say the force applied on 3 is greater than 2 and is greater than 1. Correct? Now if still you have a doubt, let us say still you have a doubt. You do a hole here, you do a hole here, you do one more hole here. What will find? Sir, this will cover like this, whereas this is how it is falling. Correct na? Stringents. So which is going more? Sir, at 3 it is going more. At 3 it is going more. That means the pressure at 3 is more than the pressure at 2 is greater than the pressure at 1. That means fluid is applying pressure. That means your fluid is applying pressure. And how this pressure is? It is nothing but because of its own weight only. Because of its own weight only, the fluid is applying pressure. How, sir? क्या बात कर रहे हो, sir? Simple से बोलो. Okay. See, you have molecules in a fluid. Molecules inside the fluid. They are what? Moving around. They are moving around. Correct. So they are colliding. Because of the collision, they are applying force. Because of the collision, they are applying force. And how that force is applied? Let me tell you. Suppose this is your container. In your container, you have fluid. We are discussing about fluid at rest. Arbitrarily, I'll take an imaginary surface. Arbitrarily, I'll take an imaginary plane. I have took an imaginary plane like this. Okay. Now let me draw this plane this side here. So I have took an imaginary plane arbitrarily. What I am finding? Okay. This is bothering you. I'll draw the diagram like this. Okay. I'll draw this like this so that at least you can see. So now the left side of the molecules which are present on the left side will apply a force on this side. That is your F perpendicular force. And the molecules which are on right side, they are also applying a force, okay, perpendicular to the surface. Let us say this is dF, this is also dF, the area is dA. The area is dA. Now, the molecules on the left side are colliding and applying a pressure here. Remember, this is an imaginary surface. This is an imaginary surface. The molecules on the right hand side, okay, they are also colliding and applying a pressure here. Okay? And these two pressures are equal and opposite. These two pressures are equal and opposite. Why, sir? Otherwise, it would have started acceleration, na? Otherwise, it would have been moving, na? If there is a pressure difference, there is a force difference, then it would have gone, it would have accelerated. But here the fluid is at rest. So condition of equilibrium is satisfying. Hence both the forces are what? Both the forces are same, equal and opposite. Applied on area dA. Applied on area dA. And how these forces are acting? Perpendicular. Remember, pressure, fluid pressure is defined as the force exerted by the fluid per unit surface area. Force exerted per unit surface area. And how the force? Always a direction normal or perpendicular. Normal or perpendicular. Why is a normal and perpendicular? See, when the fluid is at rest, there is no shear force, there is no tangential force. So the only one force, that is your which force? Which force, Baba? Normal force. So what if I apply an external force and I'll try? Then you have to take the vertical component of the force. Okay? Then you have to take the vertical component of the force. Okay? From here we came to know, okay, the pressure P, the pressure dP is equal to dF perpendicular per area dA. Let us say the area is a finite area and the force distribution is equal all around. So I will write the pressure is nothing but perpendicular force per unit area. So what is your pressure? Perpendicular force per unit area in contact. That means this liquid column will exert a perpendicular pressure on the bottom surface as well as on the walls of this container. This will exert a pressure. Okay? This will exert a pressure. So now this fluid pressure is exerted in a direction normal to the surface area. Now see, this pressure which is acting is perpendicular to any surface in the fluid, no matter how the surface is oriented. If the surface is horizontal, it will be perpendicular to horizontal. If the surface is vertical, it will be perpendicular to the vertical. If the surface is inclined, it will be perpendicular to the inclined surface. That means irrespective of the orientation of the surface, the force applied or the pressure exerted is always and always perpendicular. Hence, it do not have any intrinsic direction. There is no definite direction of the force whatever applying, of the pressure what is applied. That is, pressure is equal in all direction. And the force applied is perpendicular, no matter irrespective of the orientation of the surface. Hence, pressure is which quantity? Pressure is scalar quantity. Pressure is which quantity? Pressure is a scalar quantity. They ask in exam. Okay. Sir, why so big deal about pressure is a scalar quantity? See your force. Force is which quantity? Vector. Area is which quantity? Vector. Force and area both are vector quantity. Formula wise both are vector. But pressure is which quantity? Scalar quantity, because it did not have a intrinsic direction. Okay. So even if force is a vector quantity, area is a vector quantity, your pressure is which quantity? Pressure is scalar quantity. Okay? Pause the video and note it down. Okay, I am going to erase it now. We will read now the units and dimension of the pressure. Now we are going to read the units and dimension of the pressure. So I will request you to pause the video and note it down. Now pressure equal to your force per unit area. So I am writing P equal to perpendicular force per unit area. Force, sir, Newton. Area, meter square. What we call Newton per meter square? Pascal. Based on the name of the scientist, Blaise Pascal. Okay. He is a French scientist. He has done tremendous work okay, in your fluid statics and fluid dynamics. So to honor him, the name of the what do you call, the unit of the pressure has been kept as what? Pascal. Okay, so 1 Newton per meter square equal to 1 Pascal. Going to higher unit we call 1 bar is equal to 10 to the power 5 Pascal, small b. 1 bar is equal to your 10 to the power 5 Pascal. This is the unit. If someone has work experience, you will be knowing all the pressure measuring devices. Either they will write in kg per centimeter square or psi. What is the full form of psi? Pound per square inch. In US, Europe, you will go, you will find this unit. PSI, pound per square inch. PSI. Okay. Normally our SI unit is Pascal or bar or Newton per meter square. Now we'll go for the dimension of this. Okay. So force per area. Pressure equal to force per area. What is the unit of force? Sir, unit of force is Newton. Area is meter square. What is the dimension of Newton? Sir, it is kg meter per second square into 1 by meter square. Meter cancel. So what you got? Kg by second square into meter. That is m1 L minus 1 T minus 2. m1 L minus 1 T minus 2 is the dimension of pressure. Understood? Blaise Pascal, a brilliant guy. You know, at the age of 12, he was having dinner, and he just took out his plate and knocked it. Obviously, it has some sound. Based on that, he wrote a paper about vibration, sounds and vibration. A very brilliant guy, died at a very early age. I think 39-40 years old he died. But he has done a commendable work in your hydrostatics and hydrodynamics. Now, I'll request you to pause the video and note it down. Okay? So, now let's study about the hydrostatic law. Okay? Now, first we will consider a beaker or a container which has some fluid in it. Okay? Or you can even consider a free surface and you can go ahead with this. Okay, I want to stick to this. Okay, let me take a small area of dA. What is this area? Sir, area is dA. Okay, area is A. Here also A, above also A. So this particular block is at a depth of h. Let us say the height of this block is dh. Height of the block is how much? dh. Okay. Now we'll draw its free body diagram. We'll draw. So this is your block, dw, self weight of the block acting downward. See, this block is made up of nothing but what? Your fluids only fluids. Okay. So here your pressure P, dP, mainly P into area is A. So the pressure force acting on the upward surface is P into A. From the downward surface, the resistance, how much it is getting? P plus dP into A. And the weight is acting vertically down. So weight is what, your sir? M into G. Mass is what, sir? Density into volume into G. Okay, that is density into volume, sir. Volume is area into H. What is the height here? dH into G. So if I will take common rho A into G, what it left? It left with dH. Okay. Now same thing. Go for the equilibrium. Condition. At equilibrium condition, what happens? Summation of Fy is 0. Forces on the y directions are 0. Summation on the forces y. So what you got, sir? Pa plus your dw minus P plus dP into A is equal to 0. So what I got? Pa minus dP into A is equal, okay, plus dW. dW how much I got? Sir, you got rho A G into dH is equal to 0. So PA gone. Okay? PA gone. Now take this on the right hand side and multiply in minus on the both the sides. So what you will get? Sir, dP into A is equal to rho Ag into dH. A cancel. So what you got? dP is equal to rho G dH, or dP by dH equal to dP by dH equal to what you got? Rho into G. This is nothing but your what? Hydrostatic law. What hydrostatic law said? He said it signifies that pressure in the static fluid increases in the vertically downward direction. Vertically down, we'll come to that. See, if we'll integrate this, if we are gonna, two cases are there, let me come there. So this is nothing but your hydrostatic law at a rate equal to specific weight of the fluid. What is rho into G? What is rho into G? Gamma. Remember, rho into G we have also studied in our module 1 chapter 1. Specific weight. What is gamma? Gamma is the specific weight. So at a rate equal to specific weight of the fluid, it decreases in the vertically downward direction. That means if you go down, what happens? If you go to vertically down, what happens to the pressure? It increases. What if you go vertically up? What will happen to the pressure? It will decrease. Hence there are 2 points here. That is dP by dH is equal to rho into G when you are taking how? Vertically downward, and dP by dH is equal to minus rho into G when you are taking it as what? Vertically upward. So if this H I will take from vertically upward, like this, if I will go, I will get a minus rho G. That means in such case pressure will decrease. If we are going like this, pressure is increasing. So this is not vertically downward. As the depth increases, what happens to your pressure? Pressure also increases. Pause the video and note it down. We will go for it 2 cases. This is valid for incompressible as well as compressible flow. This is valid for incompressible as well as your compressible flow. Okay. Shall I erase? Okay. See, I am erasing now. I am erasing this. So we got dP is equal to we got first, if you take for incompressible flow, so your dP is equal to rho G dH, integrate on both the sides. dP is equal to integration of rho G dH, take it 0 to H. Here I am taking atmospheric pressure. Oh, you no need actually, because this is dP dH, there is no variable. Dopey, directly you can integrate. If you integrate, what you got? Your P is equal to rho G H. P equal to rho G H. That is in the vertically downward direction, H. So how this profile, how this relationship is? The relationship is linear. Here the relationship is what? Your linear. Okay? Understood? I doubt whether you understood or not properly. Okay? Now if I will go for your compressible flow, remember we can derive it but not required. The compressible flow, the relationship will be exponential. The relationship is going to be exponential. Okay. In case of a incompressible flow, the relation between pressure and depth is linear. In case of a compressible flow, the relationship between pressure and depth is what? Exponential. Pressure and H is exponential. Okay? Okay? Good. Pause the video and note it down. Study how the pressure varies as we go down and or in horizontal case. Okay. So first case is when we go downwards, like vertical. Okay. When as we go down, how the pressure varies. So we have already seen that. Yes, that only I want to little bit explain more. Okay. Now what you do is you take here an imaginary cylinder. What you take? What I am asking you to take? Sir, you ask us to take an imaginary cylinder. Okay, there is an imaginary cylinder. So the pressure here is P naught, that is your atmospheric pressure. This is at a depth of h. This is at a depth of h. Okay. Let us take the area on both the cases A, and I am expecting the fluid is at rest. There is not more changes there. So whatever the imaginary cylinder I have took, it is in static equilibrium condition. Okay. And the weight acting vertically downward. Weight acting vertically downward. Now what we'll do is, let's draw the free body diagram of the cylinder. If I draw the free body diagram of the cylinder, okay, W vertically downward, here pressure acting is P naught, okay, area is A, and here the pressure is P plus some dP into A. Okay, same at equilibrium condition, summation of vertical forces are 0. That means P naught A minus here P naught plus dP into A, P naught into dP, P naught plus dP into A, plus W is equal to 0, plus W is equal to 0. What is our motto here? Our motto is to find what is the pressure here. We want to find what amount of pressure is acting here. Okay? I want to find the pressure at this point. What will name it? Sir, we will name it T. Okay. We want to find what is the pressure at T. Okay? Okay. So what we know? Sir, P naught A minus P naught A minus dPA, okay, plus W, that is weight of the fluid, is equal to, that is W, weight of the fluid is equal to 0. Weight of the fluid is equal to 0. This total is, or I can write this total is PA. Correct? Correct. Okay. Let me do this. This total P naught plus dP I am writing as my pressure at T. So I'll write like this. P naught minus A equal to Pt into A plus W is equal to 0. Plus W is equal to 0. Very good. Now P naught A plus W is equal to P2 into A. Sir, how much is W? Weight of the fluid acting vertically downward, M into G. M is density into volume into G. Okay, density, sir, density equal to cross sectional area into height into G. So what you got? Pt into A is equal to P naught A plus rho A G H plus rho A G H. Take common A from everywhere. What you got? The pressure at point T is equal to P naught plus rho G H. P naught plus rho G H. So rho G H is nothing but pressure due to liquid column of depth H. So this is the pressure due to liquid column of depth H. If you want to write it more generalized, more standardized, what you write? Atmospheric pressure. Normally we are taking atmospheric pressure, atmospheric gauge pressure as 0. So I can write clearly P is equal to rho G H. P is equal to rho G H. That means pressure can be very conveniently described in terms of H. Pressure can be very conveniently described in terms of height H. If this is an incompressible flow, then rho into G will be constant and H is the only thing which may vary, and this variation will lead to change in the variation of pressure. That's why we call it as what? Head. We call it as what? Head. Which head? Pressure head, not our head. We call it as pressure head. This H, we call it as a pressure head. ठीक है? समझ में आ गया? But look at this. This equation reminds me of one more equation. That is y is equal to mx plus c. Y is equal to mx plus c. If I just reshuffle this equation, my PT is equal to rho GH plus P naught, where rho into G is your M, X is the H, C is the P naught, Y is the PT, or simply I am writing here P. Okay, or simply I am writing here the pressure P equal to rho GH plus P naught. Now plot it. Okay, what is your X? H. Okay, what is your Y? P. So if I will draw the graph between P and H, rho what we are getting? This is a which equation? Straight line equation. This is the equation of a straight line where this much value is P naught, and what is the slope? What is the slope? Slope equal to tan theta is equal to M equal to what? Your rho into G is your slope. That is your specific weight. What we call rho? Specific weight. That is for an incompressible fluid, pressure varies linearly with depth. Pressure varies linearly with depth. For an incompressible fluid, pressure varies linearly with your depth. That means if depth increases, pressure increases. If depth decreases, pressure decreases. This is which case? Which case? Vertical case. This is which case? Vertical case. Okay. Now we'll go for the horizontal case. Okay. Pause the video and note it down. Note it. Very good. Now in horizontal case, these many things are not required, because in horizontal case your pressure will come same only. Your pressure will come what? Your pressure will be same. Okay. See this now. We'll go for the which case? Horizontal case. Horizontal. Okay. Same. Draw the diagram. Okay. Same. Draw the diagram. We have a fluid in a container. Now we'll take an imaginary cylinder, but this time horizontal. But this time how will take? Horizontal. So what will be the pressure here? P into A. What is the pressure here? Sir, P into A. Here let us say here B. Weight acting vertically downward. What is this? H. Correct. Is there any depth of the column in the vertical direction? Is there any depth of the column in the vertical direction? No. So your pressure at A will be equal to your pressure at B. So if you go horizontally, any place, what you'll find? Your pressure to be same. Your pressure to be same. But provided you have the same fluid. You have the same fluid, means same density. If your density is constant, H is already constant, so pressure at all points in the horizontal plane is what? Same. Horizontal plane is same. I hope you understood this now. Okay? Okay? Pause the video and note it down fast.